Okay, let's do this. Alrighty, the distance you go around the track, 400 meters. Now the time, be careful, you want to write the time in seconds. So that is 65 seconds. That is fine if you want to leave it as a fraction. It makes sense to me. If you want to divide it out, that is meters per second. Now the displacement, remember, kind of weird, even though you're still running. If you start and stop in the same place during the course of that interval, we say your velocity is 0. All right. Okay, hang time. I like these. Let's see how this is doing. Marshall. Okay, so 125 centimeters. That is 1.25 meters. That is the distance. In fact, I like to call that our vertical distance, our distance y. So this is the equation we're going to use. We're treating this as a free fall problem. So the distance is given. We can continue to use our acceleration due to gravity. So that acceleration up and down, that acceleration vertically, we can use that number. The time is what we need to find. Time is everything. Really, once you know time, you really can then start to figure out how fast things are going to go. So remember, the whole principle with these hang time problems is you jump up in the air. When you get to the top, you do have to stop momentarily. We know the distance he climbed, and that distance is the same as the distance he would fall. All right, and the time it takes to climb is the same as the time it would take to fall. All right, so solving for this, really what we're doing is we're solving for all of the down component of its motion. So your initial velocities are 0. The final velocity is what we're going to find, but that also is the same thing as our launch speed. All right, so to solve this, 5t squared, divide that 5 through, and then you can get that square root. Square root, don't forget square root. And so remember, that's the time to fall. So really that's what we solved for there, is the time to fall. Remember the hang time, then the hang time would be about a full second. All right, up and down part. Okay, but that's not the question. The question was, how fast is he going? All right, so step 1 was to get that time. We still have some more work to do. So I'm going to use this equation to figure out how fast he was going. All right, I got a little bit of space there I'll use. Okay, our accelerations are 10. Your delta V, and this is the whole key right here, your delta V is final minus initial. And we divide that by our time. So really, we got our 10. We're solving for the final. Initial is 0, so that drops out. And the time, we had that. But hopefully it's easy to see. And hopefully you remember that shortcut a lot. But yeah, if you know the time, multiply by 10, and you can get how fast it's going. All right, so yeah, so 5. So 5 meters per second would be that launch speed. That launch speed to lift yourself over a meter up in the air. Okay. All righty. Okay, ooh, Pattonville. A lot of us have been over there. They border our district. They have one of the nicest pools in the area. I think they've even had some Olympic diving qualifying there. They've had a lot of people from around the country have come to use Pattonville High School. Okay, so they have a 10-meter platform. Question here is find the time. Okay, I guess I'll rewrite this, just helps to look at it. Our distance is 10. Our acceleration is also 10. And we want to figure out how much time that takes. Yeah, so we're just assuming like the diver's just falling. They're just standing on the edge and they just fall. So our initial velocities are 0. Just take your time when you solve this. Let's really divide that 5 through. So really it's 2. So our time here is going to be square root of 2. All right, so there's how much time it would take to fall that far. Now the question is well, how fast are they going? So that impact, that final velocity is what we're solving for. Once again, it's this first equation here. Just a couple different ways maybe to look at it. But our acceleration is due to gravity as you fall. We fell for 1.4 seconds. Just multiply that across. And I will get 14. Now, be careful here, careful reading. And that's a big part of physics. It's kind of just taking a deep breath, taking your time, not trying to rush through everything. That is not miles per hour. All right, and once again, it's always kind of that sense of scale, sense of perspective that we have you do these conversions. But yeah, that speed, so if you were to fall off the platform at Pattonville, convert the meters to miles. Running out of space. Convert the seconds to hours. Okay, and you know what? In my head, I always think it's a little over double. So it's going to be around 30 miles an hour. So I don't know. I think I maybe mentioned this in class, but I've seen people fall off these platforms and dislocate a shoulder, break an arm. I've seen their eardrums get hurt. So yeah, you can get hit pretty hard by that water if that happens to you. Okay. All right. So okay, some more free fall problems. Hopefully, maybe this is helping a little bit. Okay, so let's look at number 4. The speed needed to launch a marble. Once again, what helps me on a lot of these is the picture. I like to remind myself, even when I launch things, they stop at the top. The distance, it's 50 centimeters up in the air. That's the distance it goes. Now that is half a meter. So maybe it's important to remind yourself we want to use meters here on that. The question, this is really looking for this speed at the bottom. Before you can get speed, we need to know the time. So there's always a couple steps on these quite often. Now I will list, and this is a good hint, and this is part of the reason we do this, is just getting you used to the notation, getting used to the way things look. But these are listed in the order you use them. So the first thing we did is we converted it to meters. The next thing we're going to do is I'm going to use my distance formula. Now really, we're using this, I like to say that I'm going to use this at the peak or at the top. It's really what we're doing here is figuring out how fast it hits the ground. So remember, even though these are launching problems, my advice for us is we always just look at the down component of its motion. That makes the initial the top. That makes the final the bottom. I think that's just a great way, an easy way to approach these problems. Yeah, okay, so the distance, half a meter. It's knowing that acceleration due to gravity, that's what allows us to solve these. And the other thing that allows us to solve them is making that peak position, making that initial velocity a 0. And these are always kind of weird. That's why I say just take your time. A lot of times I do see mistakes. Students kind of rush through trying to do some of the algebra. And just caution you against that. Yeah, so the square root of 0.1, and this is another thing that kind of looks weird a lot of times, taking square roots of decimals, taking square roots of fractions, it does get bigger. So okay, so there's the time. So there's that time. Then that, once again, that's the time really to fall, is what we're saying there. So the next part is, well, how fast is it going? Well, using the time, I can figure out how fast. My favorite way to figure out how fast is use our definition of acceleration. Acceleration due to gravity is a 10. We're solving for VF. Initial is 0. And the time we had. All right, so, but the other shortcut, I think a lot of us hopefully maybe kind of remember that, but that other shortcut is just multiply that by 10. So there we go. And it's kind of that sense of scale also as you do some of these, and unfortunately you don't get to play around in class. But yeah, if you did get to launch marbles, you know, just kind of keep in mind they stay in the room, they stay close to your desk, they usually stay within an arm's reach or two. So that kind of helps you think about just how fast they need to go. And the other thing, the other kind of key thing on these is even though I solved for that launch, that final speed, that impact speed, it does equal our launch speed. All right, so kind of really same kind of deal here. And really before I start asking myself or answering these questions, I like to know what answer to expect. All right, so Coach McCaffrey is actually better than the marble. So Coach McCaffrey's jumping higher than the marble. Now this one isn't asking how fast, this one is asking for total. So remember hang time is kind of my fancy way of saying total time. So that's really what the question is here. So the idea is hopefully it's kind of easy. I mean, I got my distance. So make sure you're writing that in meters. But really, yeah, that distance in meters, I can solve for the time. So hopefully maybe that looks familiar. That's just this equation. The distance to fall, initial velocity at the top, 0. So really the picture, initial velocity at the top of Coach McCaffrey's jump. Final velocity is, we don't even need to know that. Who cares? The distance is given. And once again, it's always that time. That time is everything. If you can solve for the t, if you can solve for t, it's a good skill. And really, if you're watching this, I appreciate it. Sometimes just watching people do math problems is a good way to learn. So yeah, I'm going to divide that 5, divide through by 5. Take the square root. Once again, that always sometimes looks funny for students. But yeah, taking the multiplying fractions, decimals, taking the square root of a decimal does actually get to be a bigger number. Okay, so there's the time. Now, once again, I just like to remind myself that is the time it took to fall. Time it took to fall. So I think, yeah, that should be easy. Total time, hang time, That is just double. The time it takes to go up is the time it takes to go down. This was probably a younger Coach McCaffrey. I don't know if she could hang in the air that much now. She might. It's been close. Depends how much stretching she did. All right. But yeah, still not Michael Jordan. Still not Lionel Marshall. Still not world class, if you will. But still a pretty good jump. Pretty good leap for Coach McCaffrey. All right. Now, these multiple choice, yeah, I guess we'll just kind of start going at them. Take a deep. Some of these multiple choice are problems. Some of them are just kind of definitions. But yeah, let's just kind of start seeing how these treat us. All right. Okay. We thought about calling this class. Physics with constant acceleration. And really, what we're saying is gravity. The acceleration due to gravity does not change. Just because I'm launching marbles, jumping around, throwing things, letting cars roll, whatever I'm doing, the Earth's gravity is not changing. The Earth's acceleration due to gravity stays the same. In fact, I mean, don't we always, what do we plug in? Acceleration due to gravity. I'm 10. Plug in 10, Mr. Watterson. Plug in 10. If you're always plugging in 10, you're telling me it's always constant. It's always 10. And this is tricky. I mean, acceleration is a rate of a rate. And that is a very complex idea, a rate of a rate. But we'll keep getting practice understanding what I mean by that as we go. All right, so starting from rest, the distance. Ooh, boy. So just be careful here. The distance something falls in about 1 second. Well, you know what? Don't be afraid to use our distance formula. I don't know if you remember. We might kind of come back and talk about some of this, but hello, our puppets, the Donna Janke entrance, that was about a second. So yeah, if you've been to our south lot and come in through that balcony, you drop something off that balcony, it falls for about 1 second. That is 5. So yeah, be careful there. Be careful there. The distance something falls, use our distance formula. Okay. All right, now it's how fast. So I always just kind of take a deep breath and just be careful. What's it asking for? So if it's asking for the speed, now really, I guess, how do I find speeds? Well, I've been finding speeds using this. All right, so what is our acceleration due to gravity? It's 10. What is our final velocity? I don't know. What is our time? 1. So a lot of times students like looking at equations. That's a simple way to get that answer. But yeah, remember a shortcut. If it falls for 1 second, it gets to a speed of 2. If it falls for 2 seconds, it gets to a speed of 20. So if it falls for 3 seconds, it would get to a speed of 30 and so on. All right. Now the distances. Now remember, distances are not the same thing as how fast. So number 9 here, it's another distance formula 1. But this is kind of looking at this. This is a good way to understand really what that curve on our position time graphs is really all about. So a common mistake here is a lot of times students think, oh, 2 seconds, it's going to go twice. No, be careful. It's that time factor is squared. So it has a pretty big influence on how far things are going to go as they're accelerating. So what is that? 5? That's 5 times 4. That is 20. All right, so just be careful there. When things fall for 2 seconds, none of the above. So number 9 is a little bit of a trick question. 20 meters is the answer. It's not a choice. All right, yeah, so be careful on 9. That one kind of was a little tricky there, I thought. Number 11, what do we got here? A bicyclist goes this fast for this distance, and it's constant, or no, wait, how much time? So when I'm saying how long, it's really meaning how much time. I guess we could use, we can set it up the same way we've been doing all of these questions. So number 11 here. Now, there's a few ways to go about it, but really, I guess, it's just to solve for time. You know what? We can still always use this. This is that combination equation. This is kind of that, I think it's just a useful format. So we got 480 as a distance. Check. Now, wait a minute. You're riding your bicycle at constant velocity. You're not falling. All right, this is not a free fall problem. Constant velocity, acceleration is 0. You're not changing your speed. They're riding, they want to know how much time this takes. Now, if you never change your speed, then how fast you were going initially is your speed. So once again, if you look at number 11 here, setting it up with our distance formula, it really simplifies down to this. Because when you're moving at constant velocity, when your acceleration is 0, this term just drops out. And so we're just left with your distance is your velocity multiplied by your time. We all know this. This was like our first quiz. Distance is velocity multiplied by time. That equation works great when there's 0 acceleration, when there's constant velocity. But yeah, you can look at that. That's easy to solve. Divide that 8 through 60 seconds. So 60 seconds is the answer. All right, number 12. Let's look at 12 here. If the sprinter accelerates, so every second their speed goes up by 1. Every second their speed goes up by 1. So after 4 seconds, they're going a speed of 4. We could, on 12 if you want, 12, we can do equations on 12. I can say acceleration is final minus initial divided by t. The acceleration was 1. I want to know my final. My initial is a 0, and my time was 4. So a lot of times maybe that's easy to look at, maybe not. But that's how I would solve for that final speed, that final velocity. All right, okay. All right, so let's look at this one. If a sprinter accelerates from rest, constant rate, how far? So yeah, just kind of take a deep breath. Think about what equation you want to use. All right, so we're just solving for the distance. So that distance is going to be half. Our acceleration is a 1. The time, and from rest. So that from the rest, that's our initial velocity. We're solving for the distance. You're given the acceleration, and you're given the time. All right, what is that? It's 16. 16 times half. There we go. All right. Okay, so a curve. Whenever I see a graph question, I just take a deep breath. Position on my y, time on my x. I draw a curve. That is dropping a ball from the tallest tree. That is things speeding up. That is a velocity that changes. Okay, so if we had a straight line on a position time graph, what would that do? Position, time, Okay, now that's that line I had you draw. That was our constant velocities, our constant slope. Remember, a curve is a changing slope. A line is a constant slope. It's a great way to think about that. All right, 16 and 17, these are tricky. And it really illustrates a good understanding of motion graphs. But the shortcut is if up is the positive direction. So if up is defined as positive, coming down is the negative direction. Gravity, acceleration due to gravity, is always going to be making things come down. But remember, it really is kind of up to us how we draw those graphs, how we establish what direction's positive, what direction's negative. So like on 17 here, if we define coming down the ramp as our positive direction, well then yeah, our value of gravity, our value for the acceleration due to gravity will also be a positive value. All right, so these little plus minus signs is really what kind of helps you make sense of this. So here we're saying coming down is our positive direction. So that gave us that drop in a ball from the tallest tree. Now, when we switch which direction's positive or negative, and once again, that kind of went back to all those motion graph simulations. But if we define up as our positive value, our positive direction, so that would mean if we start something and have it move to the 0 point. So yeah, this, like I said, it's kind of tough to look at. But the way I'm hoping you think about this is the slope of the tangent line starts at 0, and the slope of the tangent line gets more and more negative. The slope starts 0 and gets to be more negative. That's what we see the changing velocity for when up is our positive direction. Okay, these take a while. These are tricky, but like I said, really the thing that helps us out the most with those is that motion graph simulation. That's what's going to help with these. Okay, yeah, so which of the following is a velocity versus time? Okay, so now think about this. Things speed up as they fall. So we're going to have things speed up as they fall. Things speed up as they fall. So that's our meters per second. Now, if we're using our tape measure and measuring these things going up. All right, so this is actually asking, which is the velocity for an object in free fall. See, this is constant velocity. This is constant velocity. We need the speed, that velocity to be changing. So this is a velocity starting at 0 and becoming more and more and more negative. But that's what we see when we define that up as our positive direction. Okay. 22, which of the following? So this, okay. So this is weird. This is the acceleration graph. So we got meters per second and seconds. Which one? So that's going to be this one. And once again, this kind of goes to that if down's positive, acceleration due to gravity is also a positive value. And it doesn't change. In fact, if I wanted to put a number on there, I could say it's positive 10. Now, if we set our tape measure up the opposite direction and start measuring up from the ground, then our accelerations would be constantly at negative 10. Okay. Yeah, and those are tricky. And those, like I said, those just kind of take some time, take a lot of practice. And it's really those motion graph simulations that help me understand those. All right, I like this. So this is it's a little black and white picture of my dog, Louie. Louie's a little poodle. Louie, he's getting old, but he can still run pretty well. Now, there's a couple of ways to go about this problem. My favorite way is actually to make a graph. So I'm going to solve it that way. And then I think from that graph you can see how we use our distance equation. All right, but the graph, and like I said, I think that's the best way to solve these. So I'm just going to sketch a little graph. The graph is going to be how fast Louis, my little poodle, is moving with respect to time. So it gives us a total. I like just kind of get a little benchmark there. So 20 seconds, 15 it looks like is going to be another mark on our graph. Oh, and 5. Looks like 5 will also be on there. Okay. He said he's going to start. So we want to keep track of the speed, his velocity, over time. It starts from rest. So I can start him at a 0 velocity. Starts from rest. Initial velocity, 0. He gets up to a speed of 7. So his maximum speed here, that's about 15 miles an hour. So it's pretty good for the little guy. So what does it say? It says it takes him 5 seconds to get up to that speed of 7. And then he holds that. Okay, so that 15 actually doesn't really need to be there. He holds it for an additional 15. So he takes 5 seconds to get up to 7, and then he holds that for 15 more seconds, or a total of 20. So the key things to kind of peek at. Yeah, he gets up to a speed of 7. It takes him 5 seconds to do that. And then he holds that speed for another 15. So there's the velocity versus time graph. That shortcut, so to find how far, what distance is this little guy going to go, that shortcut we've been introducing to you is we can find the areas. We were clicking that integral button on our Logger Pro. So to find that area, I kind of divide it up into a couple spots. I got a triangle here, so I can find the area of that triangle. And I also have a little square, a rectangle portion here. So I can find the area of that rectangle too. Triangle is base times height. Half base times height. The square is just base times height. Half. Now the base, so this is just the triangle piece. The base is 5. The height gets up to 7. It's half of 35. So there's how far he runs in the first part. Now there's a triangle piece too, or I'm sorry, in addition to the triangle is a rectangle piece. And that is the rectangle goes across 15. There's actually 15 across, and it's still a height of 7. 15. So the total is you just add them up. So the total so that is our answer there. So I like the area method. To me, it's kind of an easy way to think about motion, especially when you're given the speeds or the velocities of something. You can kind of sketch a graph of it, find that area between that x-axis and your line, and that area does tell us how far it goes. Now the other way, I mean, you can use our distance formula. There's nothing wrong with our distance formula. So we can use that to solve. Now the thing with the distance formula is we have an acceleration in the first part, or a slope in that first part, and we have a different acceleration, a different slope in that second part. So if you want to use the distance formula, which I do like it, it's very useful for us, you really have to look at it in two parts. So you'll have to use it for the first interval, that first part of the little dog getting faster, faster, faster. He hits its top speed, and then he just holds it. So for those first 5 seconds, his acceleration is that slope. So remember, on a velocity time graph, the slope of your line is our value for the acceleration. So what is that? I'm going up 7 meters per second and over 5. So yeah, up 7 over 5. Rise over run. It's just an easy way to kind of count it out. So yeah, so that is our acceleration. But once again, that is just for the first interval. It's just for the first 5 seconds. So when you get that value of A, I can plug it in. It's just for the first 5 seconds. And I started, my initial velocity is 0. So what do I get there? I have a feeling I'm going to get that number, 17.5. Let's see here. Yeah. So yeah, that is the same. Now remember, that's not the total answer. That's just that area underneath that triangle. So really two ways to get the motion, the distance, and the first part. Now there's that second piece. There still is that second piece, so we can use our distance formula for that. And really what I'm going to do now is this is for from 5 to 20 seconds. So this is that additional 15 seconds, if you will. All right, now look at that. That slope is 0. That it's still moving at a speed of 7. It's just not accelerating. So that really that term drops out. So even though our time on that interval is 15 seconds, but that's going to drop out. Now there is an initial velocity though, so you got to be careful. This is where that initial velocity at time 5, my velocity is 7. So you got to pay attention to that interval we're using the equation for. So it starts at a velocity of 7 and maintains that for 15 seconds. So that's going to be the same. That's going to be the same as this. So our distance formula is the same thing as kind of using the graph, using the integral, using the area to get that answer. So I would add those two up, and yeah, so that total distance is the same there. It is that 122.5. So it is in fact adding those two is the same as finding that area. So yeah, thank you for listening to that one. But I like using little animals or people sometimes to kind of run around, I guess. It kind of helps you remember what approach to take. My personal favorite, though, is the graph. I think the graphing, the area method, is a little bit easier than using our distance formulas. And part of the reason is with the distance formula, you got one value of the acceleration for one piece. You have a different value for the acceleration for a different piece. And sometimes just finding those two slopes, keeping in mind what your time intervals are, can make using the distance formula a little challenging. All right, so yeah, thanks for kind of keeping up with these. Now, so here's one where I've just given you the graph. All right, what do we say? We got Coach Saxton. I don't know, maybe the umpire made a mistake, and so he decided to start running out onto the field. I don't know. So Coach Saxton is running out there. So what's his acceleration? That's going to be slope. So the whole key, whenever you get a graph, just take a deep breath, look at the title, think about what the y-axis is, think about what the x-axis is, Pay attention to the interval it's calling your attention to. So this is the first 5 seconds. That's what I always like to kind of make note of. All right, so I just count them out. Rise, 6. And I like to write the units. I go up 6 meters per second. I'm going to go over 5 seconds. So yeah, you can divide that out. And really, fractions work for me. Yeah. Meters per second every second. So that's the rate that the speed is changing. That's the rate that the velocity is changing. Now, also on this graph, there is a second part to the journey. So we got this 5 to 10 second interval. That's going to be the second piece of the journey here. Same idea. We're finding the slope. What is that slope going to be? Count it out. 0. It's a flat line. All right, but once again, you can still move at a slope of 0. 6 to 6. Yeah, so some students, 6 minus 6 over 10 minus 5. It still is 0. All right, now, how far? How far is Coach Saxton going to run? Well, he's running for what, 10 seconds. His velocity is changing in the first part, and his velocity stays constant in the second part. I'm going to use that shortcut method. I'm going to use our area technique. And when I do that, I divide it up into 2 pieces. I got the area of that triangle, and I got that area on the rectangle. So if you ever see Coach Saxton get up and start running, maybe you could graph his motion. And say, Coach Saxton, we're going to find the integral. We're going to figure out how far you run. So Coach Saxton, oh my gosh. Coach Saxton, what is he doing here? Okay, that's half. The base, now it's just that section. It's just that piece, so that base is 5, height is 6. So half, that's 15. So he runs 15 meters in the first part, but remember, he keeps going. He keeps going. He keeps going. So we got to find the area of this part there. All right, so another piece to the puzzle, another piece to his journey. That's just base times height. So that, once again, just that piece. So that's going over 5, up 6. So that piece has an area of 30. Yeah, so once again, he's still the total. It's still total is our answer. So Coach Saxton will run 45 meters. He might have to jump on a bicycle to go run that far. I'm just joking. No, so okay. But yeah, that makes sense, you know. Kind of running out from the dugout out to the middle of the infield or something. All right. Okay, yeah, and once again, I think that area method on a velocity time graph, finding the area of each piece is a great way to figure out where things go. All right. Okay, let's keep going. Thank you. And once again, there'll be nice answer guides and scanned versions that you can look at on these. All right, now some of you actually got to go maybe on a little field trip with Coach Keltner. She may have been cheering for you, and she got so excited that she pushed herself and launched herself up into the air. So here's the speed Coach Keltner goes up with. She stops up at the top, and then she's going to fall back down. We solve these as free fall. So our initial is 0, and our final is the 1.58. So once again, on these hang time, these things where it goes up and down, we solve as free fall. Question, okay, determine her time. All right, now really these equations are given. So this practice was kind of a little tricky where it doesn't list any hints or equations. But yeah, but a lot of times when those equations are listed for you, you can figure these out. But I like to use our definition of acceleration to get the time. So we can use 10 for our acceleration due to gravity. Our impact, or that final velocity, is given, and we are asked to solve for time. But yeah, please just take a deep breath. Take a moment to move that t over. Then it's easier to do the algebra. All right, so there's what I get for my time. But remember, it wants us to get that hang time. So Coach Keltner takes the same time to go up as she does to come back down. And that's really kind of that whole symmetry of the up and down motion that we're trying to get you to think about. And really also kind of remember you're displaced zero. So we looked at a lot of these motion graphs where things went up and down. And our displacement was zero. Okay, so yeah, there's 26, Coach Keltner. And that makes sense. Once again, these hang times, remember I always kind of go to like some of those world-class people we saw jump. Their hang times around a full second. You know, us kind of old lazy coaches here at Ladue, we just kind of hang around for a third, fourth of a second or so. All right, oh, another animal. So when I see these animals taking off, my advice is to just chart their motion. Let's just figure out how fast they're moving with respect to time, and then we can use that area. So here, so I don't know if you've been to Grant's Farm. They got these antelopes. They're kind of fun to look at. But yeah, but really we'll start all of these from rest. So from rest, from zero. So we'll have our velocities over here, times down here. It gets up to a speed of 16. All right, and it took 5 seconds. So yeah, if you've been to Grant's Farm, it's kind of fun. They'll just be sitting in the grass, and then a few seconds later, they are chasing those little trams, and they're going that's like 30, 40 miles an hour. So it's like these things can really take off. So it takes them 5 seconds to get up to that speed, and then they maintain it. They hold it. They hold that speed for 10 seconds, which is a total of 15 seconds. So just kind of be careful. There's a 10-second interval, but a total of 15. So there's the little graph. Now, hopefully maybe that looks familiar if you're kind of still watching, still getting to this piece. But I like to break it up into a triangle section, and I like to break it up into a rectangle. And we can find the slopes of both of those, or the area of both of those. Alrighty, so the area for that triangle piece, half base times height. Now the base, I go across 5, up 16. That's going to be 40. All right, then don't forget there's 2 chunks, 2 pieces to the journey. So there's a square. Base times height on that. 10. 16. All right, so total. So if they go 40 in the first piece and 60 in the second piece, 200 total. All right, yeah, hopefully that kind of makes sense to me. 10 seconds, run to 200. That, like I said, these antelopes, these are faster than people. I mean, this is like 35 miles an hour or so. So yeah, this is faster than any person. A lion, you're not going to do so well if a lion's chasing you either. Okay, same kind of deal. I like to set up the graph. I'm going to start from rest. I get up to a speed of 14. It took me 8 seconds to do that. I'm going to hold it for 10 more, which gives me a total of 18 seconds. So yeah, look at that. That same kind of pattern. You can see our triangle. You can see our rectangle. You can see where we'll get our areas. So yeah, triangle. It's half. Base times height. And I just take a deep breath. Every time I do the base, I just look at it. 8. Height, 14. Oh, gosh. 12. So that's the first piece. The first piece. Remember, they still have to run. Second piece here. Find the area of that. That's going to be, oh, that's base times height. 10. So just kind of, yeah, just take notice. There's only 10 seconds difference along the base. Still gets up to that same 14. All right, yeah, so totals. Oh, gosh. Okay, yeah, and that's kind of in that same range of the antelope. So that does make sense to me. Yeah, he's running a little bit slower, but he's running for a little bit more time. So yeah, anyway, it does make sense. It sounds pretty reasonable to me. Gosh, sorry about the headache. Okay, yeah, so when you're given these animals or these coaches, people they're sitting there, they'll accelerate, they'll get up to a certain speed, they'll hold that speed for a certain amount of time, and we want you to figure out where they end up. All right, and I think the easiest way is to graph it, find your area, and you got how far these things are going to move. All righty, so okay. Thank you for doing through this. And like I said, if you're doing this all at once, you're doing a lot. If you're breaking it up into little pieces or skipping around, that's good. A lot of people just put it on YouTube and watch it in fast time. That's good too. So, okay. Instantaneous velocities and displacements. So these things are falling. All right, so this is in free fall. So it's just falling, falling, falling. I want to know how fast is it going at this moment, at that seconds, at that moment in time, and how far is it able to go? And we're just going to assume all of these things start from rest. Okay, so first part, find the instantaneous. So this is a little tricky in the sense that really what I'm asking you to find is our final velocity. Our final velocity at that time or at that moment. That's really what that's indicating to us. Displacement, that's easy. Now these things are all falling, so really the displacement is just the distance. They're only moving in one direction. And when things move in one direction, distance and displacement are the same. Okay, so instantaneous velocity is just that final speed, that speed right at that moment. Now, maybe you could look at that, because really a lot of us know using our acceleration of 10 and an initial velocity of 0 and a time of 1 second, that's easy to see that this goes 10. So if something falls for 1 second, its speed gets up to 10. All right, we got that. Now the other piece of these is I want to know how far they go. So that is going to be 10 again, 1 second, and we're starting from rest. So that's our Donna Janke entrance. That's that south lot. It's kind of where we started this whole thing with the puppets. That's our balcony by the library. Takes about 1 second for it to fall, and it falls right around 5 meters. Now, if it's falling for a half a second more, now this is a good illustration of what acceleration really means. So if it falls for half a second more, how fast is it going? Well, it's going to be 0 over 1.5. My acceleration, remember, that's 10. So I'm just going to keep using 10s. 10 for my A. So here it gets up to a speed of 15. Now really, you can look at that pattern. I mean, look at this one. That VF is going to be 27.5. All right, so if you know the time in the air, it's pretty easy. It's pretty easy to get how fast it's going. All right, and then like I said, the other piece of these is the distance. And I just consider that plug and chug. So if it's 1.5 seconds, I plug that in. And that other term still drops out for us. So acceleration due to gravity is still the same. The only thing we're changing on these is the time. That does change. That does change how far they go. And it does change how fast it's going. Yeah, fat fingers. Okay, yeah, that makes sense. 11. So yeah, it's not, and that's the thing I kind of really wanted to point out to you, is it's only half a second more, but since it's accelerating and since it's speeding up, it's significantly more distance. All right, and then even here, this is like, it's going to be even farther. It's not linear. Remember, it's a curve if we were to make that position time graph. So you can kind of see that by looking at these distances, things fall. All right. Yeah, so really 2 parts, so just kind of be careful on that. 2 parts. First part's really find how fast they're going. Remember, you can just multiply that time by 10. The other part of that is where they're going to go. And I just use our distance formulas for those. All right. Okay. Ooh, I think we're almost done. All right. Rolling a marble down a ramp. Okay. Solve by using equations. So marble rolls down a ramp for 8 seconds. It starts initial velocity of 0, final velocity of 0.75. So this is not free fall. All right, and maybe that's kind of a thing that jumps out at me. So if it's not free fall, our acceleration due to gravity is not 10. All right, so we can't just plug in 10 on this. So to me, yeah, that's why I kind of put this question in there, I guess, to give you a hint. The first part, A is not 10. Even though it's still gravity making it roll down the ramp, it's not free fall. So our acceleration here, it's delta V over t. Our delta V is final minus initial. So our final is 0.75. Started from rest. On your mark, get set, go. The time, it rolls down a ramp for 8 seconds. Okay, yeah, I can solve that for A. It's not even algebra. Weird numbers, but once again, this is kind of a slow ramp. So it's meters per second per second. So there's my acceleration. So that's a good number. And the idea is if you know accelerations, just like in our free fall problems, if we know accelerations, we know time, we know initial velocity, we can find how far it goes. But the key on this is our acceleration is not 10. 8 seconds. And this is kind of similar to some of those mastering physics problems. I know that a lot of the ones I've given you in class have been free fall. And the mastering physics it's a little bit of both. It's some of these on a ramp and it's some free fall. All right, so there's how it accelerates and how far it goes. I like it. Now, next part, it's the same question. It's the same question. I want us to figure out how it accelerates and how far it goes. But this time I'm not going to just plug and chug. I want to use a graph. All right, so okay, we can do that. So same problem here. So this is 30b. All right, the graph. This is like little dog Louie or the lion or the antelope. There we go. So I'm going to make a velocity versus time. This is how fast they're going. How fast it goes. It got up to this speed, it said. So my meters per second. Remember, it's starting at a speed of 0, so I can start it there. Now this is just 1. This is just going to go for 8 seconds, and that's it. It's not going to level off. It's not going to maintain. It's just going to be steadily speeding up for 8 seconds. All right. So remember our original questions. It said find the value for the acceleration. That's going to be slope. Up 0.75 up over 8. That's the same. That's how we did it. What was that? Alrighty. So yeah, that is the same. That is the same thing we had before. Now the other question was figure out where. Figure out that distance. That's our area. We can do that. And we'll do this. So yeah, we got a nice little triangle there. Area of the triangle. Half base times ht height. The base, the height, that's going to be the same, I think. All right, yeah. Okay, sorry, it took me a minute. Yeah, there we go. Same answer. Same answer. So that's the whole thing, and that's just in some ways that's like that is kinematics. If we can use equations to figure out what happens to things, awesome. If we can use graphs to figure out what happens to things, awesome. And that is the foundation for kinematics. That is kinematics. But also that's our foundation for physics. So really what we talk about in physics is what makes all this stuff move. But we have to have a consistent way to describe motion, whether it's our equations, 30 part A, or whether it's graphing, 30 part B. But the equations and the graphing really are the same thing. Thank you so much. I hope this helped you, and we will call it a day.
There's a snack cart coming if you'd like to grab a snack.
Thanks. Yeah, that sounds great. Thank you.